power source of 25,000 kilovolts, 25,000 volts or 25 kilovolts, and an internal resistance of R is connected to a circuit as shown in the diagram. A current of 4,000 amps is recorded on the ammeter, and the reading on the voltmeter is 24 kilovolts, which is 24,000 volts. The resistors are labeled R, and they are identical. Calculate the magnitude of the total resistance in the external circuit. So I'm only going to worry about the external, and I'm going to say R external is equal to V over I. 24,000 is all the potential difference going to the external circuit, and 4,000 is on the series branch, main branch, and therefore I get 6 ohms. Calculate the magnitude of R. Well, 1 over R parallel, and R parallel must be equal to 6 because it's the only thing going on in there, is equal to 1 over R plus 1 over R. So I land up with 2 over R being equal to 2 over R being equal to 1 over 6, because that 6 has come in over there. And when I resolve that, I find that I get R is equal to 12 ohms. Calculate the magnitude of the internal resistance of the power source. Well, we've got lost volts, and the lost volts are going to be 25,000 minus 24,000, which is equal to 1,000 volts. And if I want the internal resistance, I can say lost volts divided by series current. And therefore, it's going to be equal to 1,000 divided by 4,000, and that's therefore equal to 0.25 ohms. Sorry, 0.25, I have to go another line, ohms. In the circuit below, the power source has an EMF again of 25,000 volts, and an unknown internal resistance. The reading on the voltmeter V1 is 24,000 volts. The story sounding very familiar, but it turns out that it's not so familiar in the end. Okay, the resistances of the voltmeters are so high they do not influence, and the ammeter has a very low resistance. What is the reading on voltmeter 2? I'm going to go with my colors. If I go from the long stick until I hit a resistor, I exclude all meters. I never put meters into my coloring in. I find that voltmeter 1 is connected across blue and green, and voltmeter 2 is connected across blue and green. So voltmeter 2 is going to have the exact same reading as voltmeter 1. Could have given it to me in volts or kilovolts. Determine the reading on ammeter A. Ammeter A is on the main branch. I now need to work out my equivalent resistance. So 1 over R parallel is equal to 1 over 90 on the one branch plus 1 over 25 plus 20, 45 on the other branch. You add that whole branch together in order to get your answer, and I then land up with working out a lowest common denominator of 90. That's a 2, so it's 3 over 90, and R parallel is equal to 90 over 3, which is going to be 30 ohms. Determine the charge through the 20 ohm resistor in 2 minutes. Now the important thing here is to work out what the current is going through there. And the first thing I need to do is I need to establish how much current, if I had an imaginary ammeter over here, would be going through. So I'm going to say I is equal to V over R. I know the V, it's going to be 24,000, we just decided on that. And the resistance is going to be, for this whole branch, 45. And therefore you land up with 533.33 amps going through there. Now if I'd like to work out the charge, charge is equal to I times T, and current is 533.33, and the time that they gave me was 2 minutes, so it's 120, and I land up with an answer of 64,000 coulombs. The next one is that determine the potential difference across the 20 ohm resistor. So now I need to find potential difference as if there was a voltmeter connected over there, and I'm going to say what is the V is equal to I times R. We know the current going through here is 533,33, so I'm going to put that in. And even though the numbers are weird in this particular example, it's not a particularly difficult example. And I multiply it by the resistance of the 20 ohm resistor, and I get 10,666,67 volts. Electrical energy is converted into heat energy in the element of a kettle or geyser. It can be shown that the amount of electrical energy depends on the current flowing and the resistance of the resistor and the time for which it flows, and that we reflect in an equation known as work done, in other words, energy transferred, is I squared RT. The current is I is the current strength, R is the resistance, and time is the current time that it flows for. The student hypothesizes that the change in temperature of the water, delta H, in degrees centigrade, will be directly proportional to the electrical energy, since work done is equal to I, at least is proportional to I squared. So the change in temperature will also be proportional to I squared for a given resistor. And then we have to follow a method, and basically we set up the circuit. We're going to have exactly 0,5 amps on the ammeter. We're going to place exactly 50 ml of water in a polystyrene cup. We're going to read the temperature of the water carefully. Note the temperature, switch the current on, let it flow for 3 minutes. Keep swirling the water so that they get a distribution of heat. At the end of 3 minutes, switch off the current and keep watching the thermometer and read its highest reading. Repeat the experiment for a new current, and another current, and another current, and each time use a fresh 50 grams of water. So you get the following results. We've got 4 different current readings. It's easy enough. We know how to square those values. We've been given a before temperature and an after temperature, before temperature and after temperature, so we've got the change in the temperature every time we start at 22 and then we carry on. Considering all the given information, answer the following questions. Firstly, let's decide what is the independent variable. In other words, what am I changing? I am changing each time the current strength. What am I measuring? I am measuring the change in temperature. What significant variables need to be kept constant? The mass of the water or the volume of the water I would be okay with. The starting temperature. Not the same ammeter and the same voltmeter, and you're past that, you're old enough. You need to come up with things that are significant to the experiment. A polystyrene cup is used in this experiment. Why do you think polystyrene is used? Polystyrene is a good insulator, and therefore it will keep the heat in. Do you think that the polystyrene cup is totally effective? Explain your answer. Probably not. It's an open cup. Only 3 sides are going to be surrounded. There's still the open side up on the top over there, and therefore that is going to not be able to be insulated. But it is better than nothing. Then it asks you to draw a graph of your change in temperature versus I squared. So it's always y versus x. So you're going to put I squared onto the x-axis. So obviously we need to have a heading graph of change in temperature over versus current. You need to have even scaling on the temperature scale, or sorry, the change in temperature scale, which only goes up to 6, and you need to have even scaling on the I squared scale, which would be read in amps squared. And then you put a best fit line through there, and after careful review, what can you conclude? That there is a direct proportionality between the two. The next one. In the photo, the mixer and the microwave are all connected to the same multi-plug. Below is a circuit diagram of the situation, and as you can see quite clearly, these are all connected in parallel with one another, and we need to make sure that the current on the main branch is not going to blow a 15 amp fuse. So a student wishes to establish if all 3 appliances can be used simultaneously. Use calculations to determine if the multi-plug circuit will be able to run all 3 at the same time. So the first thing I do is I work out what's happening on the top branch, and I say that power is equal to V times I, 440 divided by 220, and I've got 2 amps on that branch. The next one, I'm going to say 1,320 because I need to change that kilowatts into watts, divided by 220, and I am going to say that there's 6 amps on that branch, and this branch has already got 4 amps, easy peasy. Add all of those up and I get 12 amps. You need to then illustrate what you mean. 12 amps is less than 15 amps, and therefore it will not blow the fuse. The iron is used for an average of 2 hours per day. What is the cost of the electricity used if the average cost per kilowatt hour unit is 116.63 cents? Okay, so that's a number given to you in cents, not in rands, thank goodness. So we're going to first say power is equal to V times I, and the power for the iron is 220, and the current for the iron is 4, and therefore it is an 880 watt appliance. When I now would like to work out the work done, that is power times time. Power is equal to, I need to put them in for cost, I need to get kilowatt hours, so it's 0.88 kilowatts, multiplied by 2 hours per day, 2, and that is equal to 1.76 kilowatts. Sorry, kilowatt hours, because it's hours times kilowatts. And then I multiply it by this magical number over here of 116.63 cents, and I get 205.27 cents, which is, they don't tell me my answer has to be in rand, so that's a perfectly good answer, but it really does mean about 2 rand to use the iron every day.